Hey there, and welcome to Raylene Math. For a few minutes, I'd like you to think about or discuss with someone everything that you know about lines, right triangles, circles, and vectors. If you're really serious about it, you can pause the video and join us in just a few minutes. Otherwise, let's get started. Let's consider 2 points on a graph. Let's say 0, 0 and 3, 4. So once we have these 2 points plotted, there's lots of things that we might do to connect them. We could draw squiggles, or we could draw some steps to get up to this height. But one of the simplest things we can do is put a line through 2 points. And a line of best fit or a line of regression we could find by looking for the slope and the y-intercept. Now it turns out that this particular pair of points has an exact line with a slope that's equal to 1.333 and a y-intercept equal to 0. Now we can see this r equal to 1. This is just talking about the correlation, how well the line fits the points, and the closer this number is to 1, the better the fit is. As we can see, the line fits through the 2 points perfectly, and so we have r equal to 1 is a perfect fit. Now we want to consider the parent function for all lines, which is the identity line y equal to x. And in this line, to get from one point to the next, we rise 1, run 1. Rise 1, run 1, rise 1, run 1. Or we could say that we rise 3, 1, 3. Either way, we have a ratio of the rise over the run, some measurement of the steepness of the line, which is constant no matter which 2 points we choose. And in the particular case of the green graph, we have a slope of 1 over 1 or 3 over 3, which is equal to 1. If we are to change that graph a little bit, we can stretch it or scale it so that this point here, for example, this 3, 3, goes up to 3, 4. And when we scale this, if we write it as y over 4 is equal to x over 3, this is going to give us the same line as the red line, now in blue. And so this is indicating that we take the y value, we scale by 4, and we take the x coordinate, we scale by 3. So we have a different horizontal and vertical scaling. So now we can take a look at this blue line, which has the equation y over 4 equal to x over 3, or we could write it equivalently as y equals 4/3 x plus the y-intercept passing through 0. Now we don't need that 0, so we can turn it off. What we want to do now is restrict this graph to only the point 0, 0, 3, 4 so that we get a line segment, and we can do that in the next graph or the next equation by putting a domain restriction so that x is only going from 0 to 3. So now let's focus on that line segment. We can make this line segment a right triangle by dropping a vertical line from the point 3, 4 down to the x-axis. And this next line here says that the equation is going to be x equal to 3 with a restriction on the range or the set of y values for that orange graph. And this is how you write this restriction using these curly brackets and an inequality. We can also write this restricted graph not using the blue equation, but we could write it in parametric form where the x-coordinate is given by 3t and the y-coordinate is given by 4t. So the x and the y are both functions of time. And in this particular case, we've chosen the time values to go from 0 to 1. If we were to change those time values, let's just turn off that vertical line for a minute. We could change those time values to 0 to 2, for example, which makes the line segment longer. Or we could go from 0 to 3. Or we could go from -1 to 1, which also makes the line longer. And so if we consider that we have a right triangle here, we're scaling the right triangle to different lengths. So we're going to go back to the parent size of 0 to 1, and we'll zoom in a little bit, and put back our vertical line to make this right triangle. So we can see that we have a right triangle with a horizontal line and a vertical line, but what if we were to consider that that line has one point at the start point and has an arrow at the other end? Now I'm not going to be able to draw the arrow here, but you'll just have to imagine. And so that this line is pointing to the right and up. Well, then what we're talking about is a vector. And we can see this vector in another notation where we have different start points and end points. So we can actually move this vector to a starting point of 5, 0. It still indicates that the vector is moving 3 spaces to the right and 4 spaces up, so that we end up at the point 8, 4. We could change the y-coordinate as well. We could bring it down we could take the vector back to the left. Now these two vectors are just copy-pastes of each other and translated to a different start point in the xy plane. So these are called translations of each other, and these two vectors are indeed equivalent. Now we can go back to the same start point as the original blue one, but let's actually put it at, well, let's say -5, -2. And if we do that, we can see the same right triangle trying to be formed here if we were to drop a vertical line and a horizontal line across. We can do some other things to that vector. We can reflect it, we can scale it, we can translate it. But as long as the size and the direction of the vector remain the same, then we have the same vector no matter where we start and end. Okay, so let's go back to our right triangle. We're just going to put in these lines here and make our blue right triangle. And so now we can talk about how long each of these sides of the right triangle is. We can bring up a point here on the right triangle, and we can see that the base of the triangle is a distance of 3, and the height of the triangle is a distance of 4. So by using Pythagorean theorem, we know that 3 squared plus 4 squared is equal to the hypotenuse squared. 3 squared is 9, 4 squared is 16, and that adds up 9 plus 16 to 25. And therefore the hypotenuse, or the longest side of the triangle, will be 5. And so we might ask, what are the set of all the points that might have a distance of 5 away from the origin 0, 0? If we were to go along the horizontal x-axis, we know that the point 5, 0 is 5 spaces away. We could also go to the point 0, 5 along the y-axis, and that's a point that is also 5 spaces away from 0, 0. And so maybe point P lies on the line containing 0, 5 and 5, 0. Now we can write the equation of that line in the intercept form here shown in the red equation, and we see that we have the y-intercept of 5 and we go down 5 over 5 to get to this x-intercept. Another way to write that equation is in this intercept or transformational form. We see, however, that this point P does not lie on the red line, and therefore we can't say that all the points that are 5 spaces away from the origin lie on the line. We have to think of a different kind of equation then, or a different kind of graph that makes all the points that are 5 spaces away from the origin to live. So instead we come up with something like this. What we see here is we have our point P that is one point on a circle, and we know that the definition of a circle is the set of, or the locus of, points P such that P is equidistant to the center of the circle, and the center is called C. Furthermore, the distance between the center and the point P on the circle, and of course there's an infinite number of points P on the circle, we see that point P is designated by some variables x and y. Those are the coordinates that can change, whereas the center is at 0, 0, which is fixed. We know that the distance between C and P is called the radius, and that radius is a constant distance. In this particular case then, we see that the hypotenuse is the same as the radius of the circle. So the hypotenuse of the right triangle is the same as the radius of the circle centered at 0, 0 with a point that lies on the circle called P. That radius is 5 and the center is 0, 0. Now this equation looks similar to this linear equation, this intercept form of the line that went through 0, 5 and 5, 0. But it's not the same form because we don't have these exponents of 2. So if we were to expand the exponents of 2, we would get x squared over 25 plus y squared over 25 equal to 1. And so if we multiply both sides of this equation by 25, we get this equation down here instead. And this equation, if we turn it on, we see it's the same circle. And so there's a similarity between that equation and a very famous theorem, the Pythagorean Theorem, which of course was the relationship that we had for the a, b, and c of the right triangle. We had that a squared plus b squared is equal to c squared. So this is suggesting that the x is like the a, and the y is like the b, and the radius is like the hypotenuse c. And furthermore, this x is really a distance between the center point and this point 3, 0. It's really a change in x, or that run that we were talking about when we talked about the gradient or the slope. Furthermore, this y, if I rewrite it, that's really y minus 0, and that's just going to be a delta y, a change from the point 3, 0 to the point P at x, y. And so the y final of y minus the y initial of 0 gives us this delta y, or rise, equal to y minus 0, which is just y. And so I can write that back as just y here. So we're starting to see a connection between the equation of a circle and the Pythagorean theorem. And that kind of suggests why the linear equation doesn't work. We couldn't just take the 3 of the base plus the 4 of the height and get the 5 of the hypotenuse, because 3 plus 4 doesn't equal to 5, so we have to have these squares in here, which is not happening in the linear equation. Okay, so currently we have the points in the two-dimensional plane, which are identified by their horizontal and vertical positions, the x and the y coordinates, and those are relative to the origin at 0, 0. We are dividing the plane into parallel horizontal lines and parallel vertical lines, and this way of dividing the plane is known as the rectangular coordinate system. We can now divide the plane into concentric circles. Concentric means sharing the same center. And if we do that, we get a slightly different looking grid. We can see the angles in standard position starting at 0 degrees and increasing in a counterclockwise direction. And so we see also some concentric or same-centered circles. We see a circle of radius 2, a circle of radius 4, a circle of radius 6, for example, plus all the other ones, 5, 5.1, 5.2. And so this division of the same two-dimensional plane is called the polar coordinate system, much like the North Pole and the South Pole. If you're standing here at the North Pole and looking down, you would see these concentric lines of latitude. Okay, well now we're going to take a look at another point, P. And this point P is measured here currently at 5, 0. And if we increase the value of Q, the angle, we can see that the x-coordinate changes and the y-coordinate changes as a function of the angle. And so as we go around the circle, x and y change. So we've looked at this using degrees, but we can also measure the angles in radian measure. And you may need to review that a radian is the angle formed when the arc length of a circular sector is equal to its radius. And 1 radian, or rad, is approximately equal to 57.3 degrees, which is less than a sixth of a circle. If you think 360 degrees divided by 6 is 60 degrees, then 1 radian is just a little under a sixth of a circle. So what we're going to do now is change to radian mode, just so we can see a different unit or measuring system. And when we change to radians, then we're going to go around in increments of pi over 18, which is 10 degrees, just like we did for the other case. And so we just have a different measuring system with the angles of pi by 6, pi by 3, pi by 2, which is 90 degrees, etc. So let's just go back and approximate in the degree mode how far along we are for that actual blue point P. So if we kind of skim along here, if we need to go back from radians to degree mode, we can skim around. We see that point P is around 50 to 60 degrees, and to get there exactly we could just try typing in 51 degrees, 52, maybe 52.3, 52.4, 52.5, something like that. It turns out that the exact angle that we are looking for involves using trigonometry, and it involves the inverse trig function of the ratio 4 over 3. And that's about 53.13 degrees. This ratio is really familiar because it was the slope of the line segment that gave us the right triangle. We have a rise of 4 and a run of 3, and so the slope of the line is 4/3. And here we are finding it related to the angle in this triangle. When we start to notice things and we start to wonder about them, we start to think mathematically. Maybe you can connect how the angle and the slope are related to one another and put it together with the circle. Well, that's all for now. Thanks for checking out Raylene Math.